this is how we conclude, guys. If you don't conclude, then your proof is incomplete. Okay? Alright, we still have 5 more questions to go. Let's see. Let me quickly check our time. How many minutes? Oh, we're still good. We're still good. Perfect. So let's go back here. Consider the function h of x. Are we still together, guys?
Yes.
Perfect. Let's do question 5. Consider the function h of x equal to x plus modulus of x. Express h of x as a piecewise function. So part 1, we want to express. So a piecewise function, modulus means 2 things, a positive or a negative. So h of x can be written as, let's put this parenthesis. Normally we use this bracket. So it's x plus, we can take x if x is greater or equal to 0. Then the other one will be x minus. The other piece, we take a negative x from the modulus if x is less than 0. The other one takes equal to, the other one does not have equal to. All right? And then this can be simplified to, we can have the parenthesis, x plus x becomes 2x. Then if x is greater or equal to 0, then 0 there if x is less than 0. Okay? So 2 marks for that. Now, coming to this question, let's reduce this space. They are saying sketch the graph of h of x indicating all relevant points. Okay, so let's sketch. You use a pencil and a ruler in the test, in the exam. I'm just using my free hand because I don't have those, right? Okay, now we are told that for x greater than 0, the function behaves as 2y equal to 2x. So this is the origin, 0, y equal to 2x. For every, if I take a 1 on x, so the y value will be 2. It doubles. So it looks like this. It's a sketch. So you can just indicate, maybe say a 1 here will give us a 2. Then this is y equal to 2x. All right? And then maybe you can write the coordinates 2, 1. It's relevant. All right? So that's y and that's x. So when you're sketching, they check on the labeling of x's and also the neatness of the graph. Then for any other region below x, it follows the line y equal to 0. Y equal to 0 is exactly the horizontal line. So this is y equal to 0. So maybe let me just write it in a different color. So this is the graph that we plotted. The graph in red is the one that was required. Okay. So when they come here, they will check the labeling of axes, the graph, and any other relevant point. So these will be half marks altogether to give you these 2. All right. Let's move forward. Determine the domain and range of h of x. So let's start off with the domain. The domain is such that x is an element of what? On the left hand side, it stretches to negative infinity. And on the right hand side, we take all the numbers to positive infinity. Okay, there is no restriction. And the range now is the values of y, but as you can see, the minimum value of y is a 0. But it's taken, we are including. So we put a square bracket there, 0 up to positive infinity. But we don't know the actual value of infinity. It's just an idea of a large number. So we put a small bracket there. Okay, let's move to the next question, which says, is h of x even, odd, or neither even nor odd? Justify your answer in 2 marks. So to check whether the function is even or odd, we input some h of negative x. So h of negative x is equal to, if we use the definition of h of x, it's an x plus modulus of x. So where there's x, I'm going to put negative x. So I'll have negative x plus modulus of negative x. Okay? Which is just equal to, because modulus of x will convert this negative x to be a positive x. So it will be negative x plus modulus of, it's just the same. Alright? Because I was just recording throughout. It's just a weird recording. I don't know if I'll be able to truncate that piece. But anyway, coming back to our question. So the modulus of negative of x is equal to minus x plus. And remember, the modulus of positive x is just the modulus of x. But as you can see, this is not equal to h of x. Can you see that? Because h of x does have a positive x at the beginning. So, and as well, is not equal to negative of h of x. Thus, so remember, for odd, let's just define, for if a function, if f of minus x is equal to f of x, we say the function is, and if I say f of minus x is equal to negative of f of x, so this shows that the function is even, and this one, the function is odd. So as you can see, it is neither. If I put a negative x, I'm not getting h of x, so it's not even. I'm not getting a negative h of x, which is not odd. So therefore, h of x is neither even nor odd. Okay, I'm sure you guys are following. We should know the definitions of odd and even. Now, if g of x is equal to x squared, find the composition h of g of x. So h of g of x, the other way of writing it is h in brackets g of x, which is equal to, in h we are going to put g. So remember, h of x was defined as x plus modulus of x. So my pen battery was low, but let's see. So if I'm going to put it in x, remember h of x was given as x plus modulus of x, right? So if I replace where there is x with g of x, I'll have g of x plus modulus of g of x. G of x is none other than x squared plus modulus of x squared. So modulus of x squared is just x squared, so this will give us 2x squared. Okay, that was so easy. Let's move to the next. Consider the function f of x being equal to that. Define Determine the defining equation of the inverse in the form y equal to something. Clearly show your any restrictions that apply. So let's rewrite it down in terms of y. Let y be equal to the square root of 2 plus 5x. So which means that y squared, we just have to make. So you remember when we were revising, we said you can say let this, then where there is y, you put x equal to square root of 2 plus 5y. Okay, then our task is to make y subject, so it will be x squared equal to 2 plus 5y, and x squared minus 2 equal to 5y, and y is equal to 1 over 5 into x squared minus 2. Or we can just write it as x squared minus 2 all over 5. Now, the restrictions are that what are the restrictions? The restrictions are that from this, the restriction is that 2 plus 5x should be greater or equal to 0. Otherwise, we have a problem. So if we solve this, we have 5x greater or equal to minus 2. So x is greater or equal to minus 2 over 5. Okay? So the restrictions are that if we put these numbers, so the minimum number that we can put, so we want to combine all this. So then we can say the inverse is y equal to x squared minus 2 over 5 with the minimum value of y becomes the minimum value of x. So x is greater than or equal to 0. Because if we put a 2 over 5 on x, that would be the minimum value of y, and it becomes the minimum value of x. And the minimum value of x becomes the minimum value of y. They interchange. Okay? These are the two restrictions for the inverse to exist. Okay? We can revisit that. But let's try these limits quickly. We are running out of time. So then let's do these limits. So the limit as x approaches 2 of the square root of 2x squared plus 1. Normally I like to rewrite the question. Alright? So according to the properties of limits, I'm allowed to insert the limit into each part of this formula. So this will be the square root of the limit as x approaches 2 of 2x squared plus 1 all over the limit as x approaches 2 of 3x minus 2, square root of that, which is equal to direct substitution. Let's see, 2 squared, that's 4 times 2, 8 plus 1, that's 9. So we have square root of 9 over, we put 2 here, 6 minus 2, that's 4. So square root of that will give you a 3 over 2. Direct substitution in property of limits. Alright? Let's move to the next. I'm a little bit fast now. So, but remember, I'll give you a PDF of this so you can revisit. So modulus of x over x is equal to, we know it's a piecewise function. If we take the positive value of x, then it will be x over x if x is greater or equal to 0, and then we'll take negative x over x if x is less than 0. So this is just the same as 1 if x is greater or equal to 0, negative 1 if x is less than 0. Okay? Now, limit as x approaches 0 from below of modulus of x over x, coming back to the question, then is equal to from below. So from below, then we look at this guy, x less than 0, so it will be minus 1 from below. Okay? Straight away from the definition of the piecewise function. If it was plus positive here from above, then we're going to say 1. We take the above piece. So if you are approaching from below, then it becomes that. Let's try this one for small angles. Let's see. The limit as x approaches 0 of sine 5x over 3x is equal to the limit as x approaches 0 of what? We will have, remember, we want to apply the principle of small angles. Sine theta over theta is sine theta is almost equal to theta if theta is very small for small angles. All right? So, but the thetas should match. But if you look at this, we can't apply the principle because 5x and 3x are different. So what do? We say sine 5x on top, but in the denominator we factor out a 3 over 5. And then we have 5x there. Now, we introduced this guy. But then we must cancel it out, right? This is another way of writing 3x in the denominator, right? So there is no violation here. So I can factor out this 3 over 5 out. So this will be 5 over 3 instead. Then limit as x approaches 0 of sine 5x over 5x. Now since theta and theta are equal and then x is approaching 0, so these angles are very small. So this will be giving me a 1. So this whole thing, sine theta over theta is equal to 1 for small angles. So the answer becomes 5 over 3. Okay, because this whole thing, let me highlight it in a different color. This whole thing in the box will be equal to 1 for small angles. Okay, are we together, Yashna and Abigail?
Yes.
Okay, yes. Perfect. I always want to check my time so that you're saying 5 minutes and we still have plenty of questions. Maybe what I'll do, we still have to do a few more sessions, but then we'll leave the other remaining questions. I'll just send you the PDF, then you can work on the remaining questions. And then we'll start from there when we meet next. Okay? So let's do B.
Okay.
Use the epsilon delta definition of a limit to prove that the limit of 3x minus 1 is equal to 2. So you remember when we did this recently, I told you guys we start off by saying given n epsilon greater than 0, we need to find, we just need a delta greater than 0, so that if 0 is less than the modulus of x minus 1, the constant that we are approaching is less than delta, then the modulus of 3x minus 1 minus the limit, which in this case is a 2, should be less than some epsilon. Okay? Then we say, but we start off by saying this bottom piece. We start off from the end and prove until we choose a delta. So we say, but modulus of 3x minus 1 minus 2 is less than epsilon, which implies that modulus of 3x, if you remove brackets, you have something like this, right? Less than epsilon. Factor out a 3, you have x minus 1, modulus less than epsilon. Divide everywhere by 3, you have modulus of x minus 1 less than epsilon over 3. Now, this form I want to highlight for you so you can compare and contrast. This form, yes, this form, it doesn't want to pick another color, but anyway, this is exactly this form here. X minus 1 modulus is on the left and less than delta. So whatever is on the right is our delta. So we just say, so let the delta be equal to epsilon over 3. Then we start off from there until we prove this far end. That's how we do the proof. So modulus of x minus 1 less than delta, it implies that modulus of x minus 1 is less than epsilon over 3, the one that we chose. Then multiply everywhere by 3, you have 3 modulus of x minus 1 less than epsilon, and modulus of 3x minus 3, step by step, okay? And then modulus of 3x minus 1 minus 2 is less than epsilon. Therefore, you conclude, therefore, the limit as x approaches 1 of 3x minus 1 is equal to 2. Proved. It's a two-way proof.